Definite integral. Area under the curve. Introduction. Derivative. We learned the derivative of a function or of an equation of a curve, which provide us true slope of the curve, or tangent, at a particular point. The slope of a curve changes with the movement of point. The function may be circular, or oscillating, or changing its path from ascending to descending. A point where it makes a turn will either be its maxima or minimum point, and the slope of the tangent at this point on the curve will be zero. By solving the equation of the gradient function dy dx and making it to zero, we can find the maxima or minima of the curve. Y equals fx. In last videos, we have derived the derivation from first principle to make you understand the importance and logic of the derivation. In second video, we have taken the trigonometric functions and relation from derivative calculation from first principle. The derivative, the basic definition of derived function or derivative, is the instantaneous rate of change in a function of a variable f, x, with respect to its input variable x at a certain value of the variable x. The basic definition of derived function or derivative is the ratio of the instantaneous change in the dependent variable to that of the independent variable. The process of finding a derivative is called the differentiation. For a continuous function, y equals f, x, we deduced that the instantaneous rate of change at a point p, x, y is given by function of f, x plus h, minus function of f, x, whole divided by h, where h is very small, or h tends to 0. This method of adding a small quantity h to calculate the slope of the tangent is known as delta method. The derived function or derivative is referred as by first principle. Introduction to antiderivative. We learned the derivative of most of the functions. What if we know the derivative of a function and want to find out the original function? So we need to know a way of undoing the process of differentiation. The process of undoing the derivation in calculus is called antiderivative, or inverse derivative, or indefinite integral. The process is known as integration. In third video of the calculus, we have taken antiderivative, basic understanding, and its calculation from basics. The reverse of differentiation. We know the equation of a curve is y equals fx. Then, by differentiation, we can find the gradient function dy dx. Now, we are given the gradient function dy dx. Can we obtain the equation of the curve? This reverse process of differentiation is called integration. We take an example. Suppose we have the derivative dy dx equals 2x. To find y, we require a function that differentiates to give 2x. Clearly, y equals x squared is such a function, which leads to dy dx equals 2x. But there is a catch. The dy dx of y equals x squared minus 3, y equals x squared plus 1, y equals x squared plus 7, etc. is also 2x. As we differentiate, the constant vanishes, but it does not mean it is not there. Hence, whenever we integrate, we add one constant, known as constant of integration. Thus, we integrate dy dx equals 2x to get y equals x squared plus c. Constant of integration c. For a line y equals 2x plus 4, the derivative is dy dx equals 2. Now from dy dx equals 2, we find the equation of a line by integration. It will be y equals 2x plus c, which is an equation of family of lines with same slope, as shown in the graph. To get the value of constant of integration c, we need some more information, like a point on a line, or a point of intersection at y-axis. As we noted on the graph, one point on the line is 10 and 24, and the point of intersection on y-axis is y equals 4. Notation of antiderivatives. The set of all antiderivatives of a function h, x, called the indefinite integral of h, x, and is denoted by indefinite integral h, x, dx, a symbol of long stylish capital S. Indefinite integral is called the integral sign. The function h, x, is the integrand of the integral, and x is t, the variable of integration. The symbol indefinite integral of the integral is always followed by dx after the integrand, or function. Indefinite integral xxx dx. Remember derivatives and rules. We define derivative of function f, x, as f prime of x, or by dx. For a function f, x to the power of n, equals y equals x to the power of n. The derived function is f prime, x to the power of n, equals d dx, x to the power of n, equals n x to the power of n minus 1. The constant rule. For derivative d dx, k, equals 0. Note k is a constant. U and v are functions of x. Also, d dx ku equals kd dx u. The plus-minus rule. D dx u plus or minus v equals d dx u plus or minus d dx v. Finding the derivative from first principles can be tedious. This we had shown you in our previous video on differentiation, so we complied the results as standard derivatives. The power rule of differentiation, which can be set as standard derivative and written as if y equals x to the power of n, then dy dx equals n x to the power of n minus 1. Or if f x equals x to the power of n, then f prime x equals n x to the power of n minus 1. Process of derivative and antiderivative. The flowchart for calculating derivative. For, say, y equals x cubed. It is starting from input x cubed to next block of times by power of x, or times 3. This will give 3x cubed to next block of minus 1 from power, or divided by x gives the output 3x squared. The flowchart for antiderivative is in inverse operation for 3x squared. Starting from input 3x squared to next block of add 1 to the power of x, or times x. This will give 3x cubed to the next block of divided by power of x divided by 3 gives the output x cubed. Therefore indefinite integral 3x squared dx equals x cubed. Antiderivative or indefinite integrals. This two-steps process for antiderivative of power and constants is given here in blocks. Please watch them carefully and understand. derivative, and antiderivatives. Please note, the constant, or numbers, in function vanishes in derivative. So in antiderivatives, we must add a constant of integration. Note below action on constant. For a constant function, f x equals y equals c, derivative dy dx equals 0. Antiderivative, indefinite integral 0 dx equals c. For a function f x equals y equals mx plus a, derivative dy dx equals m and antiderivative, indefinite integral mx to the power 0, is presumed. Dx equals mx plus c. For a constant in a function f x equals y equals ax squared, derivative dy dx ax squared equals a times 2x equals 2ax, and antiderivative, indefinite integral ax dx equals a indefinite integral x dx equals a times x ax squared divided by 2 plus c. Properties of integrals. The process of differentiation and integration are inverse of each other, or differentiation of integration leads to same function, or we can write d dx of indefinite integral h x dx equals h x. Two indefinite integrals with the same derivative lead to the same family of curves, and so they are equivalent. Let g x and h x are two functions with same derivatives. So d dx indefinite integral g x dx equals d dx indefinite integral h x dx, or indefinite integral g x dx and indefinite integral h x dx are identical. The integral of sum of two integrands is same as sum of their indefinite integrals. Indefinite integral g x plus h x dx equals indefinite integral g x dx plus indefinite integral h x dx for any real number k. Indefinite integral k g x dx equals k indefinite integral g x dx. Also true for number of integrands. Indefinite integral k1 h1 x plus k2 h2 x plus k3 h3 x plus k4 h4 x dx equals k1 indefinite integral h1 x dx plus k2 indefinite integral h2 x dx plus k3 indefinite integral h3 x dx plus k4 indefinite integral h4 x dx. Summary of important properties. 1. Indefinite integral g prime x dx equals g x plus c. 2. D dx indefinite integral h x dx equals h x. 3. Indefinite integral d dx h x dx equals h x. 4. Indefinite integral k g x dx equals k indefinite integral g x dx. 5. Indefinite integral g x plus or minus h x dx equals indefinite integral g x dx plus or minus indefinite integral h x dx. Calculating an antiderivative is the inverse process of the derivative. But there are many standard derivative. We remember from our differentiation, which we can simply apply to get the antiderivatives. For example, d dx sine x equals cos x. The integral of cos x. Indefinite integral cos x dx equals sine x plus c. Please note a clue, but which cannot be taken as the rule. When we differentiate, dx comes in denominators, and we lose 1 power of x in derivative. While integrating, dx comes in numerator, and which increases the power of x. In most of the algebraic functions, here we remember some derivative for you. Here are some derivative of trigonometric functions. The derivative of sine x is cos x. The derivative of cos x is minus sine x. The derivative of tan x is sec squared x. The derivative of cot x is minus cos x squared x. The derivative of sec x is sec x tan x. The derivative of cosec x is minus cosec x cot x. The derivative of sine kx is k times cos x. The derivative of cos kx is minus k times sine x. The derivative of tan kx is k times sec squared x. The derivative of sine of function x is f prime x cos x. The derivative of cosine of function x is minus f prime x times sine x. The derivative of tan of function x is f prime times sec squared x. Some standard integrals. Indefinite integral a dx equals indefinite integral ax to the power of 0 dx equals ax plus c. Indefinite integral x dx equals 1/2 x squared plus c. Indefinite integral x squared dx equals 1/3 x cubed plus c. Indefinite integral x to the power of n dx equals 1 divided by n plus 1 x to the power of n plus 1 plus c. Indefinite integral ax squared plus x dx equals a divided by 3 x cubed plus half times x squared plus c. Indefinite integral ax plus b whole squared dx equals 1/3 ax plus b whole cubed plus c. Indefinite integral sin x dx equals minus cos x plus c. Indefinite integral cos x dx equals sin x plus c. Indefinite integral cos kx dx equals sin kx divided by k plus c. Indefinite integral k sec squared x dx equals k times tan x plus c. Indefinite integral exponential e to the power of x dx equals e to the power of x plus c. Indefinite integral 1 divided by x dx equals natural log x plus c. Standard integration. Indefinite integral ax plus b to the power of n dx equals 1 divided by times 1 divided by plus 1 times ax plus b to the power of n plus 1. Above antiderivative or integral is the typical integral, which comes often and can help in solving many integral, such as indefinite integral 5x plus 7 to the power of 3 dx, indefinite integral for x plus 3 to the power of 7 dx, indefinite integral square root 5x plus 1 dx. Note: whenever you are in doubt of your result, you may please verify the result by differentiation. Here in this table, we tell you some standard integrations with an example. Antiderivative x to the power of n where n not equal to minus 1 is a divided by n plus 1 x to the power of n plus 1 plus c. See example. Next, antiderivative of 1 divided by x is log x plus c. See example. Next, antiderivative of sin kx is minus 1 divided by k cos kx plus c. See example. Indefinite integral sin 5x dx equals minus 1 divided by 5 cos 5x plus c. Antiderivative of cos kx is 1 divided by k sin kx plus c. See example. Indefinite integral cos x divided by 4 dx equals for sin x divided by 4 plus c. Antiderivative of sec squared kx is 1 divided by k tan kx plus c. See example. Antiderivative of e to the power of kx is 1 divided by k e to the power of kx plus c. See example. General power rule. The indefinite integral of f a x plus b, where a, b are constants. If indefinite integral f x dx equals capital F x plus c, then indefinite integral f a x plus b dx equals 1 divided by a f a x plus b plus c. This means that the integrals can be generalized further. In particular, we consider the generalized power rule. Indefinite integral ax plus b to the power of n dx equals 1 divided by times 1 divided by plus 1 ax plus b to the power of n plus 1 plus c when n not equal to minus 1. Indefinite integral 1 divided by ax plus b dx equals 1 divided by a log ax plus b plus c when ax plus b greater than 0. Definite integrals. The set of all antiderivatives of a function h, x, is called the indefinite integral of h, x, and is denoted by indefinite integral h, x, dx. As we saw, integration of a function leads to another function and not a numerical value. It is because the integral of a function is indefinite one, and that's why we insist you calling this as indefinite integral. However, if we consider a curve from x equals a to x equals b and integrate it, we will have the integration as definite integral and we will get a numerical value. Definite integrals are important because they can be used to find different types of measures. For example, areas, volumes, lengths, and so on. If the function f(x) is continuous at every point on the interval from x equals a to b, and capital F(x) is an antiderivative of f(x) on a to b, then integrating from a to b f(x) dx is called the definite integral and is equal to f(b) minus f(a). That is, the definite integral from a to b f(x) dx equals f(b) minus f(a). Integrating from a to b f(x) dx equals f minus f is read as the integral of f(x) with respect to x from a to b is equal to f(b) minus f(a). Usually, we have an intermediate step to aid in the evaluation of the definite integral. This intermediate step is written as f(x) with subscript a and superscript b, ab. Therefore, for definite integral, we write the integral of f(x) with respect to x from a to b is equal to f(b) minus f(a). The process is carried out in 4 steps. Step 1. Find an indefinite integral of f(x), say it is capital F(x). Step 2. Write your result in square bracket. Capital F(x) with subscript a to superscript b. Step 3. Substitute a and b into capital F(x). Step 4. Finally, we have integral of f(x) with respect to x from a to b equals f(b) minus f(a). We subtract f(b) minus f(a) to obtain the numerical value. Notice that the constant of integration c would be cancelled due to subtraction. f(b) plus c minus f(a) plus c equals f(b) minus f(a). In the expression, integral from a to b f(x) dx is called the variable of integration, and a and b are called the lower limit and upper limit respectively. There is no reason but convention that number b need be greater than the number a when finding the definite integral. Take an example to understand the steps and notations. Evaluate. Integrate x squared with respect to x from 2 to 3. Step 1. Find an indefinite integral of f(x), or indefinite integral x squared dx equals 1/3 x cubed. Step 2. Write your result in squared bracket from a to b. That is 1/3 x cubed in squared bracket from 2 to 3. Step 3. Substitute a and b or 2 and 3 into f(x), or f(3) equals 1/3 3 cubed equals 9. f(2) equals 1/3 2 cubed equals 8/3. Step 4. Subtract f(3) minus f(2) equals 27/3 minus 8/3 equals 19/3 equals 6 1/3. Example: evaluate. Integrate 3x squared plus x with respect to x from 1 to 3. Step 1. Find an indefinite integral of f, x, or indefinite integral 3x squared plus x dx equals x cubed plus 1/2 x squared. Step 2. Write it in squared bracket from 1 to 3. Or equals x cubed plus 1/2 x squared in squared bracket from 1 to 3. Step 3. Substitute a and b into f, x. Or f, 3, equals 3 cubed plus 1/2 3 squared equals 31 and 1/2 f, 1, equals 1 cubed plus 1/2 1 squared equals 1 and 1/2. Step 4. Subtract f, 3, minus f, 2. Equals 31 and 1/2 minus 1 and 1/2 equals 30. Example. Evaluate. Integrate cos x with respect to x from 30 degree to 90 degree. Follow the steps yourself. Properties of the definite integral. There are a number of simple but very important properties of the definite integral. Some of these properties are summarized. It is assumed that the integrand f, x, with respect to x, from a to b, is continuous and that the definite integral, or integral of fx with respect to x from lower limit a to upper limit b, is finite. Property number 1. Integral of fx with respect to x from lower limit a to same limit a equals 0. Example. Or integral of 2x squared plus x with respect to x from lower limit 2 to same limit 2. Sad smiley 2/3 x cubed plus 1 are 2x square in square bracket fro 2 to 2. Or f, 2, minus f, 2, equals 0. Property number 2. Integral of fx with respect to x from lower limit a to upper limit b equals minus integral of fx with respect to x from lower limit b to upper limit a. Example. Integral of e to the power of 2x with respect to x from lower limit 2 to upper limit 3 equals minus integral of e to the power of 2x with respect to x from lower limit 3 to upper limit 2. Property number 3. Integral of k times fx with respect to x from lower limit a to upper limit b equals k times integral of fx with respect to x from lower limit a to upper limit b. Note it in the example. Property number 4. Integral of f(x) plus or minus g x with respect to x from lower limit a to upper limit b equals integral of f(x) with respect to x from lower limit a to upper limit b plus or minus integral of g x with respect to x from lower limit a to upper limit b. Note it in the example. Property number 5. If C is within limit of a and b, then integral of f(x) with respect to x from lower limit a to upper limit b equals integral of f(x) with respect to x from lower limit a to upper limit c plus integral of f(x) with respect to x from lower limit c to upper limit b. Note it in the example. Line and slope. Line and slope. Let's take a line y equals 2x plus 5 and calculate the slope or derivative. dy dx it is equals 2. Or by geometric method. Increase in y, 25 minus 5. Increase in x, 10 minus 0. Slope m equals tan theta equals 20 divided by 10 equals 2. Line and area. Line and area. Let's take a line y equals 2x plus 5 and integrate it from 0 to 10. Definite integral of y equals 2x plus 5 with respect to x from 0 to 10 equals x squared plus 5x to be evaluated from 0 to 10 equals 100 plus 50 equals 150. From graph, the area under line 0, 10 equals 1/2 times 25 plus 5 times 10 equals 150. It is same area under line from a to b is as provided by definite integral. Area under a curved line. Draw a curve. Y equals x squared. The area under the curve. From 1 to 3. See graph. We can get the area by definite integral of y equals x squared from 1 to 3 as definite integral of x squared with respect to x from 1 to 3 equals 1/3. X cubed to be evaluated from 1 to 3 equals 1/3 times 3 cubed minus 1 cubed equals 26 divided by 3 is equal to 8 2/3. How are we sure it is the right way? Before the integration, people tried to estimate the area by dividing it in many rectangles. Let's break the range from 1 to 3 in 4 parts at the interval of 0.5 or 3 minus 1 divided by 4 is equal to 0.5. Now focus on the graph. There are 2 ways to cover the area under the curve. Number 1. Make a rectangle from first point 1, 1, 2. The next point 1.5, 2.25, and t. Hen next 3 rectangles. The sum of these for rectangle is lower sum equals SL equals 1 times 0.5 plus 2.25 times 0.5 plus 4 times 0.5 plus 6.25 times 0.5 is equal to 13.5 times 0.5 equals 6.75. Number 2. Make a rectangle on the left. From second point, 1.5, 2.25, to the first point, 1, 1. And next 3 rectangles, third to second, fourth to third. And fifth to fourth. The sum of these for rectangle is upper sum equals SU is equal to 2.25 times 0.5 plus 4 times 0.5 plus 6.25 times 0.5 plus 9 times 0.5 equals 10.75. Note here. The area of lower rectangle is less than the actual area, and sum of upper rectangles is more than the actual area. We can clearly see that the actual area below the curve is between the 2 sums. Actual area is more than the lower sum SL and smaller than the upper sum SU. But the gap between the 2 calculation is high. We may try to break the interval in many more parts. Let's break the range from 1 to 3. In 8 parts at the interval of 0.25 or 3 minus 1 divided by 8 is equal to 0.25. Now focus on the graph. Number 1. Make a rectangle from first point, 1, 1, to the next point, 1.25, 1.56, and then next 7 rectangles. The sum of these 8 rectangle is SL equals 1. Times 0.25 plus 1.56 times 0.25 plus 2.25 times 0.25 plus 3.06 times 0.25 plus 4 times 0.25 plus 5.06 times 0.25 plus 6.25 times 0.25 plus 7.56 times 0.25 is equal to 30.7. 5 times 0.25 equals 7.6875. 2. Make a rectangle to the right from second point, 1.25, 1.56. To the first point, 1, 1. And next 7 rectangles, in same order. The sum of these 8 rectangles is SU equals 1.56 times 0.25 plus 2.25 times 0.25 plus 3.06 times 0.25 plus 4 times 0.25 plus 5.06 times 0.25 plus 6.25 times 0.25 plus 7.56 times 0.25 plus 9 times 0.25 is equal to 9.6875. Note it again. Area SL equals 7.6875 is less than the actual area is less than area SU equals 9.6875. Let's break the range from 1 to 3. In 16 parts at the interval of 0.25 or 3 minus 1 divided by 16 is equal to 0.125. Number 1. Make a rectangle to the right from first point, 1, 1, to the next point, 1.125, 1.265, and then next 15 rectangles. The sum of these 16 rectangles is equals SL plus. As given here added to is equal to 65.375 times 0.125. Equals 8.1718. Make a rectangle to the left from second point, 1.125, 1.265, to the first point, 1, 1, and next 15 rectangles, in same order. The sum of these 16 rectangles is calculated here added to is equal to 73.375 times 0.125 equals 9.1718. Note it again. Area SL equals 8.1718 is less than the actual area is less than area SU equals 9.1718. Integration towards an exact area. What we saw so far that when we increase number of rectangular strips by reducing the interval by increasing the number of rectangular strips, we noticed that the gap between upper sum and lower sum reduces. We can produce an algebraic expression to determine the near to exact area under a curve. We find a definite integral with a limit n tends to infinity and determines the area enclosed by a curve sandwiched between SL and SU such that or limit n tends to infinity SL equals area equals limit n tends to infinity SU. Here in this table, we show you our efforts to calculate with more number of strips And you can note that the gap between the upper sum and low sum decrease. The actual area is now more tightened between the two sums. We show you the same by plotting it on a graph paper. Integration towards an exact area. Formally we proceed and consider a single strip of the area under the curve of a function y equals f(x). See graph. As we divide the interval from x equals a to x equals b into n equal parts as x0, x1, x2, x3, xn. So the width of each strip, denoted by delta x, is b minus a divided by n equals delta x. The area of the lower rectangle is f(x) times delta x, and that of the upper rectangle is f(x) plus delta x times delta x. Then, the sum of the areas of the lower rectangles SL4 a less than or equal to x less than or equal to b is sigma sum over from x equals a to x equals b minus delta x fx delta x. The sum of the areas of the upper rectangles 2 is sigma sum over from x equals a plus delta x to x equals b fx plus delta x delta x. Sigma sum over from x equals a to x equals b minus delta x fx delta x is less than the actual area less than the sigma sum over from x equals a plus delta x to x equals b fx plus delta x delta x. As the number of strips n tends to infinity and x tends to 0, the area a approaches a common limit, and this leads to the integral as a means whereby we can find the required area. That is, area equals limit delta x tends to 0. Sigma sum from x equals a to x equals b fx delta x equals definite integral of fx dx from a to b. We have developed the definite integral that provides a numerical value whose geometrical interpretation is connected to the area enclosed by a curve, and the x-axis the lines x equals a and x equals b. We can now combine our results of the definite integral with its geometrical significance in relation to curves y equals x squared on a Cartesian set of axes. This we have already done in an elaborate way and depicted by a graph. Area between y-axis and the curved line, left side of the curve, y equals x squared, is the area between the curve and y-axis from y equals 1 to 9. See graph. To get this area, we have to first, we need to make x as subject from y equals f(x) to obtain the equation x equals g, y. 2. Then find the definite integral, which gives the required area. That is, definite integral of gy with respect to y from a to b. For y equals x squared, or x equals y to the power of 1/2, and limits from y equals 1 to 9. 2. Integrating to new limits. That is, definite integral of y to the power of 1/2 dy from 1 to 9 equals 1 divided by half plus 1 times y to the power of 3/2 evaluated from 1 to 9 equals 2/3 times y to the power of 3/2 equals 2/3 times 27 minus 1 equals 17 and 1/3. Or if you replot the graph of x squared equals y, or y equals square root x, and convert the limits, it will be from 1 to 9, and proceed as usual. To verify, this is the area we wanted between curve and y-axis. We follow geometric means. Number 1. Let the area between curve and x-axis is AXC. 2. And the area between curve and y-axis is AYC. Total area between curve and x-axis and y-axis within limits equals AXC plus AYC. Two. From the graph, the sum of area, AXC, green, plus AYC, pink, is the area of the rectangle, 3, 9, minus the area of the rectangle, 1, 1. Or 3 times 9 plus 1 times 1 is equal to 26. 3. We have already calculated the area between the curve and x-axis, AXC, by definite integral as 8 2/3. Therefore AYC equals 26 minus 8 2/3 equals 17 1/3. Hence confirmed. Negative area between x-axis and the curved line. If the curve y equals f, x is negative from x equals a to x equals b. See graph. Then the integral will be negative. Or area equals minus definite integral of fx with respect to x from a to b. Or area may be taken as absolute value, or modulus of, or area equals modulus of definite integral of fx with respect to x from a to b. Signed area between x-axis and the curved line. If the curve y equals f x alternates between positive and negative over the interval x equals a to x equals b, then there will be a point on x-axis or at y equals 0, say x equals c, when it changes from one side to the other side. So we first find out from function f, x, the value of x at y equals 0. See graph, and we can calculate the area in two parts with proper signage. Area equals definite integral of fx with respect to x from a to b equals definite integral of fx with respect to x from a to c minus definite integral of fx with respect to x from c to b. Let's understand. When the curve y equals f x more than 0, or it is positive, the area will be positive. Area of 1 equals definite integral of fx with respect to x from lower limit a to upper limit c. And when the curve y equals f x is less than 0, or it is negative, the area will be negative. Minus area of 2 equals minus definite integral of fx with respect to x from lower limit c to upper limit b. Therefore, the net area will be a1 minus a2. Steps for finding areas. 1. Check the function or the curve y equals f x is continuous from the lines x equals a and x equals b. 2. Sketch the graph of the curve y equals f x over the interval. 3. Please note and determine if the function intercepts x-axis within limiter less than or equal to x less than or equal to b. If yes, note the intercepts point x equals c. Then integrate y equals f x over each region separately. If curve crosses one side to another side, or region above the x-axis and regions below the x-axis. 4. Add as required positive terms. We take an example to understand it further. Find the area of the region enclosed by the curve y equals x cubed minus 1 the x-axis and 0 less than or equal to x less than or equal to 2. First sketch the graph of the given curve, y equals x cubed minus 1. Find x-intercepts, when y equals 0 x cubed minus 1 is equal to 0 or x equals 1. And y-intercepts, when x equals 0 y equals 0 minus 1 is equal to minus 1. From the above intercepts we see that y is negative in the region 0 to 1 and positive in the region 1 to 2. Therefore, the area of the region enclosed is given by minus definite integral of x cubed minus 1 with respect to x from lower limit 0 to upper limit 1 plus definite integral of x cubed minus 1 with respect to x from lower limit 1 to upper limit 2. Minus definite integral of x cubed minus 1 with respect to x from lower limit 0 to upper limit 1 plus definite integral of x cubed minus 1 with respect to x from lower limit 1 to upper limit 2 equals minus x to the power of 4 divided by 4 minus x to be evaluated from 0 to 1. plus x to the power of 4 divided by 4 minus x to be evaluated from 1 to 2, which is work out to be 3.5. Please note if we do not follow this, we get different result when we integrate. Definite integral of x cubed minus 1 with respect to x from lower limit 0 to upper limit 2 equals x to the power of 4 divided by 4 minus x to be evaluated from 0 to 2 is 2 and not 3.5 as we got in first case. Area between two curves. 1. We solve these problems by applying simple logic. 2. Check both the functions or curves. 3. Within limits between line x equals a and x equals b, both functions are on one side. That is positive or negative. 4. Two curves, do they intersect each other within the limit? 5. We break down the areas. 6. And calculate areas by definite integral independently. We show you a simple case next on graph by animating. Area between two curves f, x, and g, x. If f, x, greater than or equal to g, x, on the interval a, b, then the area enclosed by two curves and the lines x equals a and x equals b is given by definite integral of fx with respect to x from lower limit a to upper limit b, minus definite integral of gx with respect to x from lower limit a to upper limit b equals definite integral of fx minus gx with respect to x from lower limit a to upper limit b. Now, watch the animated explanation and understand. We take here an example. Find the area of the region enclosed by the curves g, x equals x plus 5 and f, x equals x squared plus x plus 1, and the lines x equals minus 1 and x equals 1. The first step is to sketch both graphs so that it is clear which one lies above the other. In this case, as g, x, greater than or equal to f, x, on limit, minus 1 to 1, we can check it on the graph. So in this case, the function g, x, greater than or equal to f, x, on minus 1 to 1, we can write the required area by definite integral. Definite integral of x plus 5 minus x squared plus x plus 1 with respect to x from lower limit minus 1 to upper limit plus 1 equals definite integral of 4 minus x squared with respect to x from lower limit minus 1 to upper limit plus 1 equals 4x minus x cubed divided by 3 to be evaluated from minus 1 to plus 1 for minus 1/3 minus 4 plus 1/3 equals 22/3. If the question had been stated simply as find the area enclosed by the curves g, x equals x plus 5 and f, x equals x squared plus x plus 1, this means that we calculate the total area enclosed by the two curves as shown in the graph, and we need first to find the points of intersection from the equations of the curves. To get the point of intersection, we solve the equations y equals x plus 5 and y equals x squared plus x plus 1, or x plus 5 equals x squared plus x plus 1, or 4 equals x squared, or x squared equals 4, or x equals plus or minus 2. Now watch it here. We can write, therefore the required area, definite integral of x plus 5 minus x squared plus x plus 1 with respect to x from lower limit minus 2 to upper limit plus 2 equals definite integral of 4 minus x squared with respect to x from lower limit minus 2 to upper limit plus 2 equals 4x minus x cubed divided by 3 to be evaluated from minus 2 to plus 2 equals 8 minus 8/3 minus dash 8 plus 8, 3 equals 32/3. Take another example. Find the area of the region enclosed by the curves g, x equals 4 minus x and f, x equals 2 divided by x minus 1. First find the area of the region enclosed by the curves y equals 4 minus x and y equals 2 divided by x minus 1. Next, we find the points of intersection for minus x equals 2 divided by x minus 1, or for minus x times x minus 1 equals 2, or for x minus 4 minus x squared plus x minus 2 is equal to 0, or x squared minus 5 times plus 6 is equal to 0, or x minus 3 times x minus 2 equals 0. The points of intersection are x equals 2 and x equals 3. We can write, therefore the required area, definite integral of 4 minus x minus 2 divided by x minus 1 with respect to x from lower limit 2 to upper limit 3 equals for x minus x squared divided by 2 minus 2 natural log of x minus 1 to be evaluated from 2 to 3 equals 12 minus 8 minus 9 halves plus 2 minus 2 natural log of 2 minus 2 natural log of 1 equals 3 halves minus 2 natural log of 2. We an example to explain the area between the curves and show you we get accurate point of intersections by solving the equations, which can be confirmed by sketching the curve. Questions: find the exact value of the area of the region enclosed by the curves g, x equals sine 2x and f, x equals cos square x over the region 0 less than or equal to x less than or equal to pi. Solution 1. Sketch the graphs of y equals sine 2x and y equals cos square x. 2. Determine the intersection points from equations of curves. Y equals sine 2x equals cos square x. Or 2 sine x cos x minus cos square x equals 0, or cos x, 2 sine x minus cos x, equals 0. So either cos x equals 0 or 2 sine x minus cos x equals 0. From cos x equals 0, x equals pi 2, and from 2 sine x minus cos x equals 0, tan x equals 1/2, x equals arctan 1/2. Therefore, the points of intersection, in terms of angles, in radians, x equals pi 2, and x equals arctan 1/2. Please observe them on the graph. Therefore, the required area of enclosed region shown in green on the graph is given by definite integral from lower limit of arctan 1/2 to upper limit pi by 2 of sine 2x minus cos square x with respect to x equals definite integral from arctan 1/2 to pi by 2 of sine 2x minus 1/2 cos 2x plus 1 with respect to x equals in square bracket minus 1/2 cos 2x minus 1/4 sine 2x minus x divided by 2. To be evaluated on pi by 2 minus arctan 1/2. We will need to evaluate cos 2x and sine 2x when x equals arctan 1/2. We will need to evaluate cos 2x and sine 2x when x equals arctan 1/2. We will need to construct a right-angled triangle for the given angle of value of x, or tan x equals 1/2. Using Pythagoras' theorem, this right-angled triangle will have hypotenuse square root 5 with base 2 and opposite 1. So sin x equals 1 divided by square root 5 and cos x equals 2 divided by square root 5. We first consider cos 2x. Using the identity cos 2x equals 2 cos square x minus 1. And from the right-angled triangle we have that cos x equals 2 divided by square root 5. Therefore cos 2x equals 2 cos square x minus 1 equals 2 times 4 divided by 5 minus 1 equals 3 divided by 5. Next, we consider sin 2x, using the identity sin 2x equals 2 sin x cos x. And from the right-angled triangle, we have that sin x equals 1 divided by square root 5. Therefore sin 2x equals 2 sin x cos x equals 2 times 1 divided by square root 5 times 2 divided by square root 5 equals 4 divided by 5. Also remember cos pi equals minus 1 and sin pi equals 0. Therefore, the required area is given by equals in square brackets minus 1/2 cos 2x minus 1/4 sine 2x minus x divided by 2 to be evaluated on pi divided by 2. Minus on arctan 1/2. Equals minus 1/2 cos pi minus 1/4 sine pi minus pi by 4. Minus 1/2 times 3 divided by 5. Minus 1/4 times 4 divided by 5. Minus 1/2 arctan 1 divided by 2. Equals 1/2 minus pi divided by 4. Minus 3 divided by 10 minus 1 divided by 5 minus 1/2 arctan 1 divided by 2. Equals 1. Plus 1/2 arctan 1 divided by 2. Minus pi divided by 4. Therefore, the required area equals 1 plus 1/2 arctan 1 divided by 2 minus pi divided by 4. Thank you very much for watching this video on definite integral and on area under the curve and between the curve. This video is made for the revision of the topic. Thanks. You can watch our other videos by subscribing this channel. Thanks.